Okay, so we're going to do empirical review. Empirical formula. I abbreviated it, formula. Video review, real quick. I hope it's real quick. And when you start talking about empirical formula, the thing that comes to my mind right away is combustion analysis. And so we're going to do a real simple one, and then we'll do a more difficult one, and hopefully we'll get you on the path that you need to do this. So if you are given a problem that says a 0.250 gram sample of a hydrocarbon, and if it says hydrocarbon, you assume that it has just H and C in it, undergoes complete combustion to produce 0.845 grams of carbon dioxide, and it also yields 0.173 grams of water, which is a normal thing. Your formula for this would be some hydrocarbon CXHY plus O2 would yield CO2 plus H2O. And so your oxygen for your carbon dioxide and water would come from oxygen in the air. So the question is always, what is the empirical formula? And so there are a few different ways to do this. And so I'll cover just one of the ways here. I would say that what makes it easy for me is thinking about what percentage of carbon is in carbon dioxide. And so you want to know how much carbon is in CO2, which it means that there's 12.01 grams per mole, let's call it grams, over 44.01 grams. So that gives you a percentage. Well, you don't times 100, but you could do times 100. And it's equal to, what did I write? As many times I did this, I can't seem to have it memorized. 27.29. So 0.2729, which is really 27.29% every single time. If you have that memorized, it's actually, I know, having gone to the reading, they're okay with you saying, hey, this percentage is, you don't have to show the calculation. Carbon in carbon dioxide is 0.2729. Then your H in H2O. Now this part's interesting because there are two H's. So it's 1.01 times 2, which is 2.02, divided by 18.02 grams, right? And this one is like 11.12. 11.21. 1121. So, which is 11.21%, if that's what you're going to do. So you have that. Once you have that, you know the percentage of carbon and carbon dioxide. So then you can know what the percentage of carbon is of the original sample, right? And the amount of hydrogen that's in the original sample, the produced amounts of carbon dioxide and water. Now, if it says that it's combusted completely, which means that all of the carbon that was in the hydrocarbon is now in CO2, and all of the hydrogen in the hydrocarbon is now in H2O. So to set this up, we would say, okay, 0.845, can't see the decimal point, grams times 0.2729. Oops, that does not look like a 9. It's a horrible handwriting, which we know already. So if we multiply those two together, we end up determining that there is 0.2306 grams of carbon. And for the hydrogen, it was 0.173 grams. And remember, this is the CO2 and this is the H2O times 0.1121. And that's going to give you 0.01935 grams. So you now know how much hydrogen and carbon there is in your original sample. And the original sample, interestingly enough, is this 0.250. So really, if we know there's only carbon and hydrogen, you actually could have done 0.250 minus 0.2306. And that should also, and I didn't do that math ahead of time, 0.250 minus 0.2306. And it gives you a number close enough, 0.0194. So sometimes you don't, if one of your elements is not one of the products listed, but you know it's one of the original elements, you subtract the quantities from the original mass, and then you can get the final element. So you can do it that way too. And I'll give you an example of that later, but let's continue with this for a second. Once you have that, that's the first step, finding out how much carbon is in the carbon dioxide that was given off and how much hydrogen, and that's from the original sample. So now we can convert it to moles, okay? So we have, let me look at the calculator here. We have 0.2306 grams of carbon, okay, and my horrible bridge. And you have 12.01 grams of carbon in 1 mole of carbon. And when you do that, that gives you 0.01920 moles of carbon. And for water, 0.01935 grams of hydrogen divided by, and this is just hydrogen, so it's 1.01 grams of hydrogen in 1 mole of hydrogen, and we get something in the neighborhood of 0.01921 moles of hydrogen. So now this is interesting, right? What you end up doing is you put the larger number on top, you divide, so if you have more than 2 elements, you divide all the elements by the smallest one. Whatever one has the fewest number of moles is the one cell on the bottom. So we're going to put carbon on bottom because it was the smallest, 0.01920 moles of hydrogen. I'm sorry. I was looking at one thing and writing another. 1 moles of hydrogen divided by 0.01920 moles of carbon. Now, basically, it's an empirical formula. You want this to be as close to a whole number as possible. Sometimes they'll give you like 2.5 or 2.3, in which case, if it's 2.5, you're going to need to multiply that times 2 to get a whole number. Or if it's 2.3, you're going to multiply it times 3 to get a whole number. Just be able to recognize that. But really, this ends up being a 1-to-1 ratio, 1 hydrogen to 1 carbon. So you end up with a CH as the formula. This is the empirical formula. And of course, this is never good enough. They end up saying something along the lines of, let me see just for a second. They would say something along the lines of, you have the actual molecular mass. So we'll call it the molar mass of the molecular compound is this. What's the molecular formula? And so you need to then divide the molecular or the molar mass by the empirical mass. So you end up with 39.06 grams divided by 13.02 grams, and you end up with 3 as the number. So 3 times CH, and your molecular formula is C3H3. So they have something like that. Let's do one more problem, or how about I set it up? And again, this is a video, so you guys can practice it. I'm going to give you the problem, and then I'll just kind of give you the answer. And if you have any problems, you can of course contact me, but I'll try to give you enough hints along the way. So you have a 0.2500 gram sample that has carbon, hydrogen, and oxygen in it. And complete combustion produces 0.3364 grams of CO2, and it produces 0.1500 grams of H2O. Okay, what is the empirical formula? Now, here's this oxygen. Remember what I said about subtracting? You can do that later. So this is the point of the video which you stop, and then you come back and check. And so you stopped. All right, let's start working this out. So for the carbon, when you do this, you end up with the 0.3364 times 0.2729 equals 0.100 grams of carbon, and the hydrogen is equal to 0.1500 times 0.1121, and that's going to give you 0.01678 grams of hydrogen, and you have the 0.2500 grams as the total, minus 0.100 grams of carbon, minus 0.01678 grams of, oh my goodness. All right, sorry, of hydrogen. And all that's going to be equal to 0.1332 grams of oxygen. So you have your 3 samples there. And again, I'm abbreviating this process. 0.100 grams of carbon divided by 12.01. So you end up with 0.008325 moles of carbon and 0.01678 grams of hydrogen divided by 1.01 gives you 0.01665 moles of hydrogen. And over here you have 0.1332 grams of oxygen divided by 16.00, and you end up with 0.00837 grams of oxygen. So we can go to the next page, and remember the smallest moles are always on bottom. And in this situation, the smallest moles belong to the carbon. So we're going to do H over C, and we're going to do O over C. So H over C is 0.01665 moles of hydrogen over 0.00835 grams of carbon, which is basically a 2-to-1 situation. And the oxygen is 0.008327 moles of oxygen over 0.008325 moles of carbon, which is basically a 1-to-1 situation. So you have with carbon H2O, which is the basic structure of carbohydrates. So if they gave you, and this, so you find this molecular mass, a carbon, so 12.01, say, I forget what it is now. I should know this by now, plus 2.02 plus 16. So 30.03. And so then they would say something along the lines of, well, what we're looking for has a molar mass of 180.18 grams per mole. So what's the final formula? Well, that divided by 30.03 is equal to 6. So CH2O times 6 equals 6H12O6. And hey, that's sugar. Hey, big shocker. Love that one. And that's how you solve that. So I'm hoping that is good for empirical formula, and that's the combustion analysis. And I hope that will help you with your calculations and your preparation for the AP exam. Let me know if you have any questions. And make sure you get some sleep. All right. Bye, guys.